So hola nerds, since that's how you say it in Spanish, because they don't have their own word for nerds. It's not very divertido of them. Ah, see? I'm not very gringo. Yeah, it's not very fun. They should have a word for nerd. Nerds are in every country. Anyway, today we are going to continue section 2.2. We're not going to finish it, but we will continue it. So please, if you didn't start the homework last night, please get on it tonight. Get started on it, because tomorrow's stuff is going to be using the graphing calculator heavily, and I don't want the graphing calculator material to bog you down in the homework. So please, if you haven't started it, get on it tonight. Yesterday we finished off by talking about the average rate of change of an equation, and that was simply just plugging in the x's, getting the corresponding y values, and finding the slope between them. And that was the slope of what we call a secant line. A secant line is any line that goes through 2 points on a curve, and its slope is the average rate of change over that interval. Today, we're going to start by using the average rate of change to try to estimate the instantaneous rate of change. Instantaneous rate of change would be, what is the slope, the exact slope at this single value? So if I can say, what is the slope at that point only? And since we don't know how to do calculus yet, the way that we can try to estimate the the instantaneous rate of change at a single value is to find the average rate of change using points around it. Our authors wanted us to use 3 average rates of change to pull that off, but I say that, you know what? As long as we pick x values that are close enough to our x equals 1, we can pull this off with a single average rate of change. What I'm going to do then is I'm going to pick x's that are very close to x equals 1. I'm going to go just a little bit before it and just a little bit after it. So I'm going to use x1 being 0.99, so I'm only going to be off by a hundredth. And I'll use x2 is 1.01, again, only off by 1/100th. And x equals 1 happens to be, the midpoint between those 2 points, right? So I am going to find the slope of the secant line that connects these two x values. And we're going to use that slope to say it's a good estimation of the actual rate of change of my curve at the single value. But I need y values to go along with these x's, so I have to plug them in. Oops. So we do have to plug them in. I've been charging my calculator for a little while. That's my power cord. I'm charging. There. Okay. So I'm just plugging in 0.99 into this equation. So 0.99 squared. Am I recording? Yes. Okay. Microphone's on? Okay, good. 0.99 squared minus 4 times 0.99 plus 5. I am not going to round this to 3 decimals because we're trying to be as accurate as possible. I'm going to actually write 2.0201. And then we're going to do the same thing, only this time we're going to plug in x equals 1.01. And again, don't round to 3 decimals. Write down the whole thing since it's a terminating decimal. Okay. Now that I have my 2 xy pairs, I can find the average rate of change between those 2 x's, which is literally just the slope between these 2 xy pairs. y2, nope, y2 I have is 1.9801. y2 minus y1, 2.0201. Over x2 minus x1. Now I did do this 4th period already, So I know that this happens to be 0.04 over 0.2. Wait, do I have it backwards? You know what? I don't know what I'm trying to do in my head. 1.9801 minus 2.0201 is negative 0.04. I'll be all right. And what is this one, 0.02? Okay. And when you do the division, we get an average rate of change of negative 2. So what we can say is that our instantaneous rate of change at x equals 1 equals negative 2. And that is an estimation. As it turns out, that is the exact instantaneous rate of change at x equals 1. Will it always be exactly right if we estimate it that way? No. It was exactly right because quadratics play nice. They do pretty friendly things, I guess you could say. As the exponent goes up higher, that would be more and more off. You'd have to get closer and closer and closer. Like maybe you have to go out to thousandths instead of hundredths to get the one that's going to be closest to the real deal. But that's all we are going to do. We're going to estimate instantaneous rates of change by using average rates of change. Your job is just get close with your x's. Cool beans? The hundredths? I mean, it's not. There's nothing wrong with going. If you went to the tenths, you could go to the tenths. It just won't be as accurate. So the closer to the number you get, the more accurate your answer is going to be. And I'm not going to, bless you, I'm not going to, if I put this on your test, it won't, if it's a fill in the blank, I'll tell you how close to get. And if it's multiple choice, I wouldn't have things like negative 2 and negative 2.1 as both options because that's just mean. I don't have a reason to do that. So I would make it so that as long as you got close, you'd know what the answer was. So this next box, which is a very large box, has a lot of information going on. A lot of information. The good news about all of this information is it's going to come up again, and we'll actually take more formal notes on it. This box is being very specific about what's going on with quadratics, but we'll have even more notes on the material that extends it to all polynomials, not just quadratics. The title of this box is Rates of Change of Rates of Change. That's not a typo. It literally means how quickly your slope changes. And slope, you can only use the term slope when you're talking about straight lines. But you just told me talk about a rate of change of a curve. Rates of change can't change. And I have an example down here for the real world, but let's just read what it says. Second order rates of change, also known as your second differences. You've heard me say first and second differences. As long as your x's go by 1, then your first differences are your rate of change, your slope. As long as your x's go by 1s, then your second differences are your also known as second order rates of change. They are the rate of change of the rate of change. For example, real world example, driving. We can describe our motion when we're in a vehicle in several ways. I could describe my position over time. So I could say my position with time as the variable. At 1 hour, I had gone 50 miles. At 2 hours, I'd gone 120 miles. At 3 hours, I'd gone 180 miles. You see, this is describing position over time. But hopefully everybody in the room is aware that distance over time is a rate, which is a speed. We could say velocity. So we could also describe the velocity of our travel. This is supposed to be as, not it. well, whatever. Velocity, oh no, velocity of travel is the rate of change of your position. Speed is how quickly your position is changing. Velocity is speed with direction. But we all know that if we step on the brake or step on the gas, our speed starts to change, doesn't it? Our velocity would start to change. Acceleration is the rate of change of velocity. So acceleration is the rate of change of the rate of change of your position. So yes, rates of change can also change over time. Why would we care? Because second order rates of change, also known as our second differences, can tell us a lot about a graph without looking at the graph. So let's take a peekaboo at what happens to quadratics. Let's see. Here I have a quadratic. It's the same image that we saw yesterday with the little circles representing zoomed in pictures of what's going on at that coordinate. Specifically though, this quadratic is facing upwards, which means our a value is positive. If the quadratic is downwards, then we know the a value is negative. But either way, what do we see? I see m equals representing my rate of change. So here what I'm seeing is a rate of change of -4. Here it's not quite a steep rate of change of -2. Here it's flat rate of change of 0, instantaneous rate of change of 0, instantaneous rate of change 2, instantaneous rate of change 4. The slope, m, is increasing as we go from left to right. You see that? -4, -2, 0, 2, 4. That's going up at every step as we go from left to right. So because the slope is increasing, because the second difference is positive, we know our graph is concave up. See, it's concave up to the left and to the right. The rate of change of the function is increasing. Not the function is increasing. The rate of change of the function is increasing. I mean, if you look here, where you have negative rates of change, that's decreasing. If you look here, we have positive rates of change, that's increasing. But the numbers themselves aren't increasing as we go from left to right, so the rate of change is increasing. The rate of change of the rate of change is positive. So if the rate of change of the rate of change is positive, concave up. If the rate of change is increasing, concave up. Okay? And I know it didn't ask us to do it, but I'm going to go ahead and show you some like table style knowledge. Again, I'm going to say if we say that our x's go by ones, and let's just pretend that here x went by ones, okay? Then our first differences would have been our rates of change. So we do it like this. So we're saying that our x's went by ones. We don't actually know the y values, but what we do know is that our first differences in y. Little triangle means delta. I don't know if you've ever seen delta be used for for change, the change in something. Okay, and that's delta 1 means first differences in my y values. Those are these. Those are m's. M's are delta 1s. They're first differences. They go -4, -2, 0, 2, 4. Oh, I didn't mean to make those so, well, whatever. I'll just come down here. What I want to do now, I didn't mean to make these lines so long, is I want to find the difference of the differences, the second differences, the second order rate of change. What do I have to do to go from -4 to -2? +2. What do I have to do to go from -2 to 0? +2. 0 to 2, +2, 2 to 4, +2. Seems like there's a pattern, doesn't there? But because my second order rates of change are positive, I know this thing is concave up. Because the rate of change is increasing, I know this thing is concave up. Cool? Okay. Now this one, the only difference is this graph points down. To the left of the vertex, look at my rates of change. They're positive, increasing. To the right of the vertex, look at my rates of change. They're negative, decreasing. But look at the numbers themselves for the rates of change. 4, 2, 0, -2, -4. Those numbers are falling over time. That means my rate of change is decreasing. The slope, m, decreases from left to right, and because the slope is decreasing, that makes the graph concave down. The slope's decreasing, meaning the rate of change is decreasing, meaning the rate of change of the rate of change is negative, concave down. So this isn't so much math and numbers that we're crunching, it's understanding what's going on with our curves. Understand what's going on with the curves. So once again, because my rates of change are decreasing, I could say my rate of change of change is negative, and both of those statements tell me my graph is concave down. So if you haven't already made the connection, concavity is tied to second order rates of change, second differences. This thing's delta 1 of y's was 4, 2, 0, -2, -4. I won't draw the vertical line since they messed me up last time. To go from 4 to 2, -2, 2 to 0, oh my goodness. Holy cow. Anybody want to make a prediction about anything that they're thinking about right now? Well, I mean, we know it's concave down because they're negative. Because our second differences are negative, we know it's concave down. Because our first difference was decreasing, we know it's concave down. I could tell you it's not an accident that these second differences were 2's. Anybody want to ask a question or make a prediction? I'm just curious to see if you were thinking. No? Well, you could ask about the third rate of change. You mean third order rate of change? The rate of change of the rate of change of the rate of change? It's a thing. It's called the jerk. It doesn't have any names after that. But the third order rate of change is called the jerk. No, you learn about it in physics, yeah. It's meter, let's see, acceleration's meters per second per second. So yeah, it would be meters per second per second per second, yeah. And the best way to describe what jerk is used for would be like acceleration of dragsters or acceleration of elevators. You guys ever been in an elevator in a standard apartment building? Yeah? Some of you have been? You ever been in an elevator in a hospital? You ever notice the difference? The ones in the hospital get up to speed a lot faster because they got to get where they're going, right? So in a hospital, you'll notice that I hate going down in hospitals because I always get butterflies the moment the cart starts. Now, they don't last very long, but there's an instantaneous moment where your stomach goes, whoa, 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 because you dropped real fast. That's a jerk that you just felt. And the same thing with when they start to go from stop to move, they have a rate of acceleration that is very quick, a rate of a rate of a rate at the very beginning that they move. And that's why they'll feel like they press you into the floor real fast. But then it lets that go also really quickly. So yeah, the jerk is third difference. They make these really great, and it's actually called a derivative, but they make these really great nerd shirts that say like, don't be a third derivative. So if you're a nerd, you get it. Like, don't be a jerk. Just me? Okay, well, I think it's hilarious because I'm a nerd. And in Spanish, I'm a nerd. All right, anyway. So this question, the authors wanted us to do some really ridiculous stuff. I don't want it to be as ridiculous as what the authors are going for. So I just want to be able to explain using real language, functions, and first and second order rates of change to talk about what we're talking about. What a weird thing to say. This first thing says, okay, the cost of a gallon of milk is increasing. My question for you is, that's not my question. My question for you is, if you said the cost is increasing, would you say that that's a first or second order rate of change? First order rate of change. And the reason why we can say it's a first order rate of change is literally because, and this is what's in our textbook, the cost of 3 gallons of milk is what you get if you multiply the cost of 1 by 3. 1 gallon by 3. So that's the proof that they demonstrate, the proof that they use to demonstrate that it is a first order rate of change. So we know it's a first order rate of change. And what I can say is we can have a function of price over time. So cost of gallon of milk can be measured as, actually it's not cost of gallon of milk, but cost of milk. Cost of milk can be measured as a function of number of gallons purchased. And that's how we can prove that this is a first order rate of change. However, if we say that the rate at which milk prices are growing is increasing, and here's what we know. We all know that the price of milk is growing. We know that. Okay? But the rate at which it's growing is increasing. Is that first or second order rate of change? Second order rate of change, yeah. And the reason why we know it's a second order rate of change is because we can talk about the slopes of this graph's secant lines. The slopes of this graph's secant lines are getting steeper and steeper over time, which means the rates over average rate, the average rates of change are increasing over time. I'm actually going to write out average rate of change. So average rate of change of the cost function that we just mentioned in green. How about average rates of change of the cost function are increasing over time. So now we're making a new function where we plot slopes versus time. Mm-hmm. It's not so much composition. It's, I mean, I see what you're getting at, trying to make the connection. It's taking, how about, let's do it like this. Let's say we had a function, right? And this thing's function is cost equals price times number of gallons, right? So if you bought 5 gallons, your price is 5 times 1 gallon, right? So cost equals 5 times X. Okay. Now, if you were to graph that, it's going to be linear, right? I'm trying to, now if we were to graph the cost of a single gallon over time though, not over the number of gallons, but over time, the cost of a single gallon is now your Y value, whereas this one's Y value was cost. This one's y value would be the cost of a single gallon, where its x values are time. And this will not be linear. It'll be curvy. In fact, it'll curve up like exponential. So what that means is every time I find an average rate of change of a secant, it's getting more and more steep. So it's not so much a function within a function, it's more like, man, I'm struggling to not use calculus terms.
It's okay, I'll just accept it.
Okay, you'll just accept it? All right, but know that at this one we're plotting slopes over time, whereas this one we're plotting cost over number of gallons, okay? I'm going to read you what the authors wanted me to say. It's way too much. So for the first one, with the whole cost of a gallon of milk increasing, I could say, when I could have said per gallon of milk, the per in price per gallon suggests a rate, and the price of 10 gallons of milk is 10 times the price of 1 gallon, but the function of interest is the price of milk, not in dollars, but rather in dollars per gallon, and the price of milk is a function of time. Time as the input is suggested by the word increasing. The input variable is time, the output variable is price per gallon. First order rate of change, the function is increasing over some interval of time, thus the rate of change is positive, but we have no numerical value for this change in price of milk over change in time. The second order rate of change, now there's no information or context clues about this given, and the graph would have a positive slope and could be concave up or down. That was all just for that first thing. Just for you to be able to justify why you know it's a first order difference or a first order rate of change. Yikes. There's no reason to read the other one. I think you get the idea of how ridiculous that is. I need you to understand whether or not it's first or second order. And if this was going to end up being a test question on your mid-chapter test, it would say something like, is this scenario describing a first or second order rate of change? And how do you know? And it would just be a sentence. First order, because I could measure the price for several gallons as a multiple of the price of 1 gallon. Done. Cool with that? Yes, Mr. M? Fantastic. All right. Do you guys remember the cereal box question? Where our store was selling boxes of cereal and they were figuring out how the demand for the boxes of cereal changed over time? Or not, excuse me, not over time, but over cost. We found out that as the price of the box of cereal goes up, the demand for the box of cereal goes down. We got this equation here that showed us that if the cost was 0, we could give away just over almost 74,000 boxes of cereal. This slope indicates that every time the price of the box of cereal goes up by $1, the demand decreases by about 15,000 boxes. Bless you. Okay, you guys remember that? Great. So this is that same cereal box question. It does have an extra digit though. Fat fingered the keyboard apparently. This 4 shouldn't be here. I just typed it by accident. I'm sorry. Negative 15,358.93 is what that should have said. Had an extra digit in it. Anyway, this cereal box demand model from our last lesson was this, where X is the price per box. So then what was Y? Y was the number of boxes sold, also known as the demand. So we know a price per box, we plug it in, it'll tell us roughly how many boxes of cereal we can sell at that price point. Yes? This question says, use this model to develop a model for the weekly revenue generated from cereal sales. But what is revenue? Money in, money out, money in. Revenue is money in. That's why I'm going to write it in green. Money in. Tell me, how do I get money in? Well, you're not wrong, but that's not what I'm asking. I mean, it's like in general, how do I calculate the amount of money that comes in? That's a better question. Let's say it like that. Well, that profit is going to be revenue minus costs. So I want to know, how much money do I make when I sell my boxes at a certain price? The question is, how do I calculate the money I make? The money that comes in, I should say. For example, if I sell hats for $10 a piece and I sell 20 hats, what was my revenue? $10 a piece and I sell 20 of them, what's my revenue? 200, how'd you get that number? Oh, multiply. You mean the number sold times the price per item? Okay, so revenue is the number of items sold times the price per item. So what is our revenue equation? Our revenue equation, well, the number of items sold was Y, and the price per item was X. Y times X. Oh, but I have an equation for Y, don't I? It's right there. Negative 15,358.93x plus 733, 622.50 times x. If you distribute this x, you have a negative quadratic, which means we can maximize that. Its maximum is going to be found at its vertex. So we have a way of maximizing our revenue as a store. So do we need to sell more boxes or do we need to bring in more money? What's more important? Bringing in more money. So sometimes it's better to increase the price of an object, even though it's going to lower the sales, because it will increase the revenue. Again, this is the kind of thing that industrial and civil, well, not so much civil, but industrial engineers do for companies. They figure out ways to maximize revenues while minimizing labor costs and man hours and cost of the goods, cost of the packaging, cost of the shipping, a lot of that kind of stuff. We will use our technology to maximize this. So on our graphing calculator, we're going to go to y equals. So on y equals, and you will notice I already have mine typed. So you need to go ahead and type yours. The hardest part about something like this kind of question is, what's your window going to look like? Well, let's talk about it. What's the smallest number for x that we would want to see on our window? 0. And so if I go to zoom 6, it drew a quadratic. I know it's hard to tell, but it went right through 0, 0. Well, of course it did, because if x is 0, the whole thing is 0, 0. But look at there, it went to the left of the number 5. So on my window for my x-axis, I'm just going to go from 0 to 5. Because my maximum is somewhere up there. See how steep that line is, though? That maximum revenue is up there, folks. It is up there. So go to window, go from 0 to 5, and your y minimum, well, your revenue is going to be greater than 0. We know that. But we kind of want this thing to land on the screen. Someone give me a number to go for my maximum revenue. 50,000? So one of you said 50, one of you said 80, one of you said 100. If I go to 100, then at least I can say I encompassed all the other answers, and my y scale, I'll have it go by 10,000. I just divide my maximum, min to max by 10, and then hit graph. Boom. And 100,000 is actually a really good estimate. Actually, 80,000 is not large enough. 80,000 is not large enough. It was close, but you would still have to have raised it in order to see the answer, right? So if I go to 80,000, it'll chop the top of my graph off, which means I have to go higher. 100,000 is a good estimate. Second trace maximum. Second trace maximum is number 4. Hey, you guys want to see something that I actually learned recently from Miss Hamill? You know how it says left bound? You could either scroll left or you could just type to the left. Can we see? You guys can see that the answer is that somewhere between 2 and 3, right? You see that? I'm going to hit 2, enter. And it says right bound. I'll hit 3, enter. It says you want to take a guess? And I'll say sure, 2.5, enter. So you can type them rather than scrolling left and right and hitting enter. It'll still tell you what the right answer was. You have to guess. No. You're guessing where you think it's close to because the calculator is doing some really high-end estimations. Your guess has to be between the two numbers that you said. And if your graph is not upside down like mine is supposed to be, you missed your negative sign on your slope. Somebody said, why is mine upside down? Anyway, this is the maximum revenue. Just over $88,000 per week at this price per box. And when you try to round this to, we don't round money to 3 decimals, we round money to 2 decimals, you know, pennies on the dollar. So this will be at $2.40 per box. So the max revenue of $88,226.73 at $2.40 per box. It's how much money came into the store. Because it didn't tell us how many boxes we sold at that price. If you wanted to know that $2.40 per box, we could go back, or we could just plug it in right here to see how many boxes we would have sold at that price. In fact, why don't we do that? Negative 15358.93 times the price of 2.4 plus 73,622.5. We would have sold 36,761 boxes of cereal that week-ish at $2.40 per box. And out of curiosity, what was that, $2.40? So as it turns out, we did maximize our revenue at that price. We had no way of knowing that with this information. I mean, we could have multiplied each and every one of those and seen, but we had no way of knowing that that was the ideal, optimal price for a box of cereal for our store. Not because it sells the most. No. Because the quantity times the price brings in the most. So yeah, that's what's up. And that's a really good stopping point, because this question uses technology and then goes on to talk more about it. So we'll call it right there. Gracias, nerds.